This is review video number 5, all about gravity and circular motion. So we're going to start with gravity. And one of the basic things about gravity is that any two objects, or any object with mass at all, will attract any other object with mass. So if this is Earth, and you have a little satellite out here beyond Earth, okay, Earth is attracting that satellite, but the satellite is also attracting Earth back. Now obviously, the force that the satellite is applying to Earth is going to affect Earth different than the force that Earth is exerting on the satellite. But that force is the same. Okay? The force from the satellite on Earth is the same as the force from Earth on the satellite. So if we were to look at gravitational fields around Earth, they would all be pointing towards the center of mass of Earth. Now, if these were actual field vectors, so if we are close to Earth, let's say at a point here, then gravity is much stronger. If we're further away from Earth, say out here, then that gravitational field will be much weaker. So remember, the length of those vectors represent the magnitude as well. Now, one of the things that we need to start out with gravity is mass versus weight. Okay? Often confused for each other. Remember that mass is the amount of matter. Okay? And we measure that in kilograms of matter. Now, mass is one of those things that whether you are on Earth or on the Moon or on Jupiter, it's not going to change. The amount of matter that makes up you stays the same. You still have the same number of molecules in your body, no matter where you are. Now, weight is the force on your mass due to gravity. So, if you're on Earth, you have a certain weight, and we measure that in newtons. You go to the Moon, you have 1/6 the weight that you do here on Earth. So let's say that your mass on Earth is 50 kilograms. Okay, so your weight would then be the mass times the acceleration due to gravity on Earth, which puts you at about 500 approximately newtons. Now, if you go to the Moon, okay, you would still have the same mass, but now your weight on the Moon would be that 50 kilograms, but there's about 1/6 the gravity on the Moon. So that means that we are looking at, roughly around 1.6 meters per second squared for an acceleration. Okay? So that gives you right around, right around 80-ish newtons. So that's a significant drop in how you would feel, the force that you would feel. You still have the same amount of mass, but the force that you feel due to gravity is different. You go to Jupiter, and Jupiter has 11 times the gravity that Earth does. So you would feel 5,500 newtons. Okay, still have the same mass, still take up the same amount of space, still have the same amount of matter, but that force acting on you is significantly greater. Now when we look at gravity, okay, on the surface of Earth, we can say that the force of gravity is just mg on the surface. But if we're looking at two objects and how they're attracted to each other, or if we're talking about things that are further away than simply the surface of Earth, we need to use this equation. It's in your reference tables. Okay? Where our force of gravity equals our gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them. This is just the distance. Okay? It's not half the distance, it's not like a radius. Okay? Now the reason why it's used as r is, let's say this is Earth and this is the Moon. Okay? this would be r, the distance between them. But really, it is the diameter. If we sketched out the orbital path here, it would be the diameter of the orbital path. But it is the distance, it is not the radius. So now, one of the things people forget all the time is that when using this equation, they tend to just plug g in instead of the actual value, which is 6.67 times 10 to the negative 11th, and then there are units. It's a Newton meter squared per kilogram squared. You have to remember to plug in the units even on those constants. On the cover of your reference tables, it tells you some distances, like from Earth to the Sun or Earth to the Moon. That is center to center. Okay, you don't have to include the radius of any of them. That is center of mass to center of mass. Sometimes people get confused if it's a question about an attraction between the Earth and the Moon. They try to add in the radius of Earth and they add in the radius of the Moon. You don't need to do that. Now, if we look at that equation a little bit further, sometimes what they'll ask us is, how does the force of gravity change if we double the mass? Okay, so let's say that this is twice as much up here, but everything else stays the same, so we can just plug in a 1 for that value, because it's not changing. Okay, so if we double that mass, our force of gravity is going to be 2 times that original force. Sometimes they'll ask something like, what if we double the radius? Okay, so we double this, everything else gets put in as a 1, don't need to worry about it, and it becomes 1 over that doubled radius, but that 2 has to be squared here, so it's 1/4 the original force. Okay, so make sure that you, for those types of equations, that you adjust each value appropriately. Now, on to circular motion. Okay, so if this is our circular path, so you know what, let's do this right. If this is our circular path, here is the center of that path, and this is our object traveling around that path. Now, if it's a car or an object on a string, whatever it may be, there has to be some sort of device or force that's making it travel in that circular direction. We call that the centripetal force. If it's a car, it's the friction between the tires and the road. If it's something that's tethered, it's the string or whatever else is tethered there. And that centripetal force is always towards the center of the path. Okay? That means if our force is in that direction, our acceleration, our centripetal acceleration, is also in that direction. Our velocity is tangent to that path. So that if we let go of the string or we lose friction between the road, it's going to travel, its inertia is going to take it in this path. Okay, that's its inertial velocity. Now its speed can be constant going around the circle, but its velocity is changing direction. So now if that object is up here, now its velocity is heading this way. So the velocity changes direction, but the speed stays constant. Okay? So now if we take a look at the equations that go along with this, some of the equations that you'll see are the centripetal acceleration, which is v squared over r, and v being the speed at which it travels around the circle, r being the radius here. So you're just simply squaring that velocity or that speed and dividing it by the radius. The other equation you might see or need to use is Fc equals mac. Okay, our centripetal force equals mass times centripetal acceleration, which if we plug this in here for that, we get mv squared over r. The mass is the mass of the object right here, whatever the mass is that's going around in that circular motion. And then again, the v is the velocity or the speed as it goes around the circle, and r is the radius. Sometimes, if they want to get real tricky, actually, let me just do a new slide here. What they might do is they might say that the period to travel around is 2 seconds. And they might say that the radius is 2 meters. And they'll say, find the velocity, find the speed. Okay? So in this case, we can use basic geometry to find the circumference, which is the total distance all the way around. Okay, and to do that, circumference equals pi d, or 2 pi r. Okay, we know the radius. So that circumference is the total distance that it's traveling, and the period tells us the time. It takes 2 seconds to go all the way around. So we can find the velocity by doing circumference divided by the period. Okay. That's kind of one of those things you just have to work out if you get to that type of a question. Otherwise, just make sure that you know the directions of the velocity and the forces. The force and the centripetal acceleration are always towards the center of the motion. The velocity is tangential. Okay, and just know that if we let go, let me get rid of some of this here. If something happens to this string that's holding this object on, it's going to head this way. Sometimes last year, like, is it going to hit here at A? Would it go to B? Would it go to C? Or would it go to D? Just make sure that you know it travels off in that straight path, or would it go to E even? Okay. Any questions? Let me know.